Welcome to Empowered Learning. This video will be the first video in a video series on techniques of integration where we will address trigonometric substitution. So in this section, we will learn how to deal with expressions of the form square root of a squared minus x squared, square root of a squared plus x squared, and square root of x squared minus a squared, where a is considered to be a real number that is positive, and we will be integrating all of those expressions that I've just read. And so we particularly want to do that because normally in these situations, use substitution does not work. And so what we do is we notice that these forms of the radicand all sort of mimic a trigonometric identity that we're used to seeing that comes from the fundamental trigonometric identity. And so we exploit that fact to be able to rewrite our expression under the radical, aka the radicand, in such a way to where we can totally get rid of the radical sign altogether. Okay. Now, the byproduct of doing that is that we have some extra baggage that we have to deal with. And in particular, if we do some kind of trigonometric substitution to basically get rid of, let's say, this expression here, and we get it as something that doesn't have a radical in it, then the baggage comes in what the equivalent of dx is in terms of that trig substitution. And so the examples that we're going to do here are actually going to address that and show us how we can navigate through that. So I'm going to scroll down here in the notes and show you what the suggested substitutions are. So for our square root of a squared minus x squared, where again, a is considered to be a positive real number here, we can either use x is equal to a times sine theta, where theta is understood to be angles in between negative pi over 2 and pi over 2. And that's because of the fact that if we're using this substitution, then we also have to be flexible to be able to use the inverse of sine sometimes as well. And we know that sine inverse is only defined in quadrants 1 and 4. And hence, these are the angles for that. So we could either use that, or we could use x is equal to a times cosine theta. And again, all this comes from the fact that we know that 1 minus sine squared is cosine squared, and 1 minus cosine squared is sine squared. And so if we could replace, in this first example here, x is equal to a times sine theta, then we will essentially have a situation here where our radicand ends up just being cosine squared theta. And of course, square root of cosine squared theta will be absolute value of cosine theta. And we'll assume in most of these cases, and I'll get a little deeper into why this is, that would just end up being cosine theta. Or in other words, we'll look at only the non-negative cases of cosine theta. So if we were to do the a times cosine theta and then replace everything, then we'll see that we get sine squared theta as a result. And of course, square root of sine squared theta inevitably will just be sine theta. And of course, that makes that part easy. But again, I would have to take the derivative of a sine theta and a cosine theta. And of course, that is what I would use to be able to replace dx. And that's where it gets sort of interesting in how we actually maneuver in evaluating these integrals. Okay. Now, similarly speaking, if we have square root of a squared plus x squared, then of course, the suggested substitution comes from the fact that 1 plus tangent squared is equal to secant squared. And we see that this x squared here looks like tangent squared. So that's why we would use a times tangent theta to substitute x. And so again, tangent is also has an inverse that's defined only in quadrants 1 and 4. And so that's why we would make sure that we identify that. But again, with tangent, we know that negative pi over 2 and pi over 2 are not included, whereas with sine, negative pi over 2 and pi over 2 are included. Now, if we had an expression that looks like this, square root of x squared minus a squared, then the fact that we know that secant squared minus 1 is tangent squared, which is just basically this equation above, just rearranged, then we could use x is equal to a times secant theta. And of course, we know that secant and its inverse only operate in quadrants 1 and 2, but we exclude the angle pi over 2 whenever we're dealing with that. And so these are suggested substitutions. And so from that, once we do these substitutions, what we have to do is see what is it that we have left. And after we see what we have left, then we'll have to do some simplification and then use other techniques to be able to eventually get to our answer. So I'm going to start off going over one example that's already worked out. And then the rest of the examples that we'll do will be ones where I haven't worked them out yet, and we will go ahead and find the answers from scratch. So with our first example here, we see that we are asked to find the most general antiderivative, or evaluate the indefinite integral of x cubed divided by square root of all under the radical x squared plus 9. And so we see that our denominator here has this form of square root of a squared plus x squared. So we already know that whenever we see this, the suggested substitution should be x is equal to a times tangent theta. Okay. And so what I've done here is sort of organically just kind of back into it. But the important thing here is that we're going to use this suggested substitution here. So if you want, you can kind of ignore this part. We don't necessarily have to do that, but I know when I worked the problem, it made sense to me to kind of show that, hey, this is why we're actually making this substitution here. So I stated if we let, but because we already know the given substitution should be, we're going to let x equal 3 times tangent theta. And so because of that, if I was to take this situation here and let x be that, then that means when I come back here, if I let this x be 3 tangent theta, then I'm squaring that, which would be 9 tangent squared theta, then plus this other 9 right here. And then, of course, I can go on to rewrite that, and I'll see eventually I get the 9 plus x squared. So my point in doing all this again was just to show that, hey, if I do this substitution here, I would still end up getting the same thing that I got under the radical. Okay, so we go ahead and say, all right, we'll use that substitution. But if we do that, then of course we have to take the derivative of this as well. And so the derivative of x with respect to theta will just be 3 times secant squared theta. So that means that our dx here is going to be 3 secant squared theta d theta. Okay. So in the grand scheme of things, the thing that is most important here is that x is going to be 3 tangent theta, and that dx is going to be 3 secant squared theta d theta. All right, so in noting that, we're going to go ahead and officially now let x equal 3 tangent theta. So we substitute that all in. We see it here. I factor out the 9, and I know that tangent squared plus 1 is going to be secant squared. And of course, this 9 that's here, I can break it out as a separate square root. And of course, square root of 9 is 3. And so what we end up having here is 3 times secant theta. Okay. Now, one thing I do want to mention here that's a little subtle is that this is actually absolute value here, okay? So anytime you take the square root of something squared, that is actually absolute value. But we go ahead and we say here that we end up having just 3 times secant theta because of the fact that whenever we do this substitution here, one of the things that we're assuming, even though we're not explicitly saying it here, we're assuming that x is going to be a positive number, okay? And so part of the reason for that is in how we're going to be dealing with these angles that are associated with the substitution that we're dealing with, okay? And so to make things simple, we're going to assume that x is positive, which is going to allow us to say this. Now, of course, if our values of x were negative, then we would have to, adjust for that. But it's going to turn out here, and this is probably the simplest way I can explain this, that since we're saying that x is equal to 3 times tangent theta, then this is what we're actually saying here, okay? And remember that tangent theta, in terms of right angle trigonometry, is talking about the sides of a right triangle, okay? So remember, this is opposite side of a right triangle over the adjacent side. And of course, this x value here is referring to the side of a right triangle. And of course, that side has a length, and length is always non-negative. And so whenever we do this substitution here, that's one of the subtle things that we're actually assuming to be able to get through the substitution and get to what we want, okay? It's not terribly important to remember that unless you're actually using these results to do something with it. But just want to let you know that's why here we actually end up with just 3 times secant theta, okay? All right, so once we do all that, then it's just a matter of plugging in everything, doing some simplifying, and seeing what we get and working with that. So we see that we have integral of x cubed divided by square root of x squared plus 9 dx. We go ahead and substitute what x is here, and then of course that's cubed. We also substitute what square root of x squared plus 9 was, which is just this 3 secant theta. And of course our dx was up here, the 3 secant squared theta d theta. So we do all that, and we see we have a pair of secants that reduce themselves to 1. And we have some other simplification that's going on. And once we do some more simplification in this step, we see that we essentially get down to here. And so this should look familiar to you, because if you're studying trigonometric substitution, then that means you should have already studied trig integrals. And so this is a situation where we have tangent raised to a power that's 3 or higher times a secant, and we know how to deal with that, okay? And so in this case here, because we have, because tangent is odd here, what we want to do is break out another tangent so that we can write it this way. And of course, the purpose of that is that now that we have secant times tangent here, we know that the derivative of secant is secant tangent. So we have, if we were going to do u substitution, we have everything here to have du. And for this tangent squared, we know that we could rewrite that to be secant squared of theta minus 1. So if we let u equal secant theta, then it's going to turn out that du is all this stuff I've circled here, okay? And so that's exactly what we end up doing. So we rewrite tangent squared, let this secant tangent d theta all hang out. U is equal to secant, du is secant times tangent times d theta. And we just substitute all that in. And so you see that we get this simple polynomial here, u squared minus 1, that we have to take the antiderivative of. And of course, that would just be 27 times, in parentheses, u cubed divided by 3 minus u, plus some integration constant. We distribute the 27 to both terms, do that, plus c, and then we go back, substitute, stating that u was actually secant theta. Okay? And so this ends up being our answer, but it's our answer in terms of theta. We need our answer in terms of x. So what we have to do now is go translate and say, all right, well, what is going to be secant theta in terms of x? Well, if we keep on going here, notice that we've already written x to be equal to 3 times tangent theta, which is another way of saying that, again, tangent theta is equal to x divided by 3. And if we look at this from a right angle trigonometry standpoint, here's our angle in quadrant 1. Here's the opposite side of the angle. Here's the adjacent side of the angle. We know that the one thing that's missing is the hypotenuse. And if we use the relationship in between the sides of a right triangle to figure out what the hypotenuse is, then it's just going to be square root of 9 plus x squared, okay? Which that looks familiar to us because that is what our denominator was, okay, in the original problem. But the main thing here is that now that we have the relationship of tangent theta with respect to these, the ratio of these sides here, what we also can do is find out what any of the other trig functions relationship is going to be. So we have tangent, but I can also read this and figure out what secant is, okay? And if you remember, secant is the reciprocal of cosine. So if cosine is 3 divided by square root of 9 plus x squared, because this is going to be adjacent over hypotenuse, then of course secant is going to be the reciprocal of that, which is hypotenuse over adjacent side. And so that is what you're seeing me state here. So we have a way of being able to express secant in terms of x here. And again, we are assuming that secant theta is going to be positive here because of the fact that when we look at this, all these refer to sides of a right triangle, okay? And we know length has to be non-negative in this case. So to make all that fit, then of course we have to assume that this particular expression is positive, and then we go and substitute in secant theta for this expression here. And so once we're done, you see that after we do a little bit more algebra and arithmetic, that we finally get to this answer here, which is 1/3 times square root of x cubed plus 9 cubed, and then minus 9 times square root of x squared plus 9 plus the integration constant, okay? Okay, so now we are going to move on to examples to where we'll actually work those out from scratch. And so with this first example here, we want to integrate 1 over x squared times square root of x squared minus 225. And the first thing that jumps out at us here is if we rewrite this, that this looks kind of like this, where this value of a is going to be 15, because if a squared is 225, then that means square root of 225 is 15. And so in that, we see that this is fitting the suggested substitution here, where we should have x is equal to secant theta. And in particularly, forgot to write the a there. So the suggested substitution here should be a times secant theta, which in this case is going to be 15 times secant theta. Okay. And so we kind of already know that if that's the case, then x squared minus a squared, I'm just going to go ahead and write it out, square root. If we go ahead and let x equal to 15 times secant theta here, then this is going to be 15 times secant theta, and all that's going to be squared minus 15 squared. Well, that lets me know here that if I wanted to factor out the understood 15 squared in both of these, because this 15 here, since I have a square here, will be 15 squared times secant squared. So this will be 15 squared like that. And then we'll have secant squared theta minus 1. And of course, we know that secant squared theta minus 1 is just tangent theta, or tangent squared theta, rather. And of course, all of this just ends up being just 15 times tangent theta. So what we're seeing here, this square root of x squared minus a squared, if we use this substitution here of x equals to 15 secant theta, then of course that expression in the denominator just ends up being 15 times tangent theta. And so now that we have that, we're going to have to fill in everything else. Okay. In other words, we need to figure out what x squared will be. And we also need to know what dx is going to be. So if we know that, then therefore, I'm going to go ahead and find dx first. So we know that the derivative of x with respect to theta is just going to be 15 times secant theta times tangent theta, which means that our dx is going to be 15 secant theta tangent theta d theta. Okay. Now, we also know that x squared here is just going to be whatever this is, the 15 secant theta squared. So that would be 15 squared times secant squared theta, which is just going to be 225 secant squared. And that 5 was running away from me there. So now that we have all of that information, we can go and substitute all that in, okay? And just to make sure that we're all on the same page here, we know that this dx is now going to be this 15 secant theta tangent theta d theta. We know that the square root of x squared minus a squared, we've already figured that out. All of that is just going to be 15 tangent theta. And of course, this x squared here is just going to be 225 secant squared theta. Okay. So now that we have all that, we'll just go ahead and substitute all that in. I'll switch colors here. So therefore, we have integral of dx, x squared times square root of x squared minus 225. And that is just 15 secant theta tangent theta d theta all over 225 secant squared theta times 15 tangent theta. And so now we just need to simplify all of that. So here we see that we have this 15, and this 15 will reduce to 1. We have this tangent, and that tangent will reduce to 1. We have this secant and one of these secants reducing to 1. And so all we have left here is 225 times secant in the denominator and d theta in the numerator. So we know here that if we have secant in the denominator, that's the same thing as having cosine in the numerator. So here we could rewrite this as 1 over 225 integral of cosine theta d theta. Okay, and then of course from here looks like it's easy going because we know that the antiderivative of cosine is just sine. So we have 1 over 225 times sine of theta plus c. And so that would be our answer in terms of sine, but we need to figure out, well, what is going to be our answer in terms of x? Okay, we have it in terms of theta, but now we need it in terms of x. So to do that, we go back to our original substitution here, which was x is equal to 15 secant theta, okay? So here I'm going to put not done yet. So here, if we make us a little right triangle here, the angle theta, and we remember here that our value x is the same as 15 times secant theta, then that is the same thing as saying that x over 15 is the same thing as secant theta, which that's another way of saying that cosine is 15 divided by x, or adjacent over hypotenuse. And so now that we know what the hypotenuse and the adjacent side of the angle is, we could use the relationship in between the three sides of a right triangle to figure out what this third side is here. And I'm just going to call it W for now. So we know that 15 squared plus W squared will equal to x squared. Okay. And so when we are done looking at all of that, we'll see that W just ends up being square root of x squared minus 15 squared, which is the same as 225. And so that should look familiar to us because we saw this square root of x squared minus 225 in our original problem here. So here I'm going to erase this W and rewrite it with square root of x squared minus 225. And now we see that sine of this angle theta is just going to be square root of x squared minus 225 divided by the hypotenuse, which is x. Okay. So here, but sine of theta is just going to be all of this. So we can now finally say that our final answer, and we'll start off with what the problem originally had, which was this. And what we ended up with was this 1 over 225 sine of theta plus c. And then finally, we just replace sine with square root of x squared minus 225, all that over x plus c. So this concludes this example and part 1 of this video series. I have 3 other examples that I want to work out, but I'm going to save those for the next video. And so we'll start with the example B that I had in these notes at that next video. So hope to see you there.